This session of chemical bonding and molecular structure is about molecular orbital treatment of heteronuclear diatomic molecules. In the previous session of MOT, I spoke about homonuclear diatomic molecules. In this session, I am going to talk about the species whose atomicity is 2, diatomic. Atomicity should be 2 atoms. And they are heteronuclear, 2 different atoms. Examples. So, carbon monoxide I am going to consider, and nitrogen monoxide I am going to consider. I am going to consider NO plus. So, we will discuss about MOT of these 3. So, if you observe CO, NO plus, of course, all these are diatomic. Atomicity is 2, and these 2 are different atoms. Carbon is 1 atom and oxygen is 1 atom. Nitrogen is 1 atom and oxygen is 1 atom. 2 different atoms we have. Therefore, these species belongs to a category called heteronuclear diatomic molecules. Of course, the last one is ion. As we know, ion is formed by either loss of electron or gain of electrons. So, we will see in ion also, in the molecules also, how we can explain the MOT. Using that, one can explain the properties of molecule. The very important concept is energy level diagram. So, let me explain a bit about the energy level diagram of homonuclear and how it is going to be different from heteronuclear. So, now we will see what is the actual concept of sp mixing and no sp mixing, and later we will see what is the change in energy level diagram in case of heteronuclear diatomic molecules. As we know, in case of 1s and 2s atomic orbitals, there is no change, or just we write bonding molecular orbital, anti-bonding molecular orbital, and will fill the electrons. The changes occurs in case of if the 2p atomic orbital is going to be interfered. So, let me draw that one. So, now I am going to draw the molecular orbital including only sp. I want to draw 1s and 2s. I am going to draw only the molecular orbital of 2p only. So, as we know, 3 2p atomic orbitals will overlap with another 3 2p atomic orbitals, so that 6 molecular orbitals are formed. So, these are the 3, 1, 2 and 3. This is of 1 2p I consider, and 1, 2, 3, this is of the 1 more 2p. These are the 2 different 2p atomic orbitals of respective atoms. So, out of 6, 3 are anti-bonding. So, this is the fashion how we draw the anti-bonding molecular orbitals, and remaining 3 are bonding. So, bonding we draw the molecular orbitals in this fashion. So, let me name this. So, this will be sigma 2pz, and this will be pi 2px, and this is pi 2py. These 3 are BMO, and ABMO we mention star. Therefore, this will be pi star 2px, and this will be pi star 2py, and this will be sigma star 2pz. So, out of 3 BMO, 1 is sigma and 2 are pi. Out of 3 ABMO, 1 is sigma and 2 are pi. So, try to know out of 3 p atomic orbitals, 1 is going to form sigma bond. So, let me explain why you get 1 sigma bond and why you get 2 pi bonds when the p atomic orbitals are going to overlap each other. So, let me consider this fashion, this kind of energy level diagram already we have seen. So, this will be in the x direction if I consider, and this will be in the z direction, and this will be y. Similarly, I consider this will be x, and this is the y coordinate, and this will be z coordinate. The shape of a p atomic orbital is a dumbbell, whereas s is spherical and d is the double dumbbell we know. So, here if I draw a dumbbell in the z direction, that stands for pz, isn't it? So, I will consider one more atomic orbital which is in the z direction. So, since there is head-on overlapping, isn't it? So, here we have a lobe and here also we have a lobe. Since there is head-on overlapping of pz atomic orbitals takes place, therefore, always pz will be sigma, whether it is bonding or whether it is anti-bonding. Therefore, 2pz I have written sigma here, and 2pz I have written sigma star, since head-on overlapping takes place in case of pz. So, in the same diagram I represent a px. This will be the px, okay, and this will be the px. So, now PX-PS, this orientation is in this fashion, this PX orientation is in this fashion, so head-on overlapping is not possible. Then sideway overlapping takes place. So this is how the one lobe of PX is going to overlap with one lobe, and one lobe of PX is going to overlap with that one, so that a pi bond is formed. Therefore 2px we write pi, and pi star 2px we write that is also pi. What about y? So in this direction we have y, that will be the dumbbell shape, and in case of y also there is no head-on overlapping, there is sideway overlapping. So y atomic orbitals I overlap, so that is also pi. Therefore pi 2py I have written. So this is the reason actually why we write pz sigma and px py pi. We know this concept, and using that also we have drawn the molecular orbital theory. But one more kind of energy level diagram we considered. So let me explain that, because when you talk about heteronuclear diatomic molecules, that is completely different. So it is very important to understand what is the change and why the change is going to occur. So this is the MOT I am going to draw for 2p. It is of the same. And now let us assume this is the energy level diagram for a lighter. So 3 atomic orbitals we have here, and 3 atomic orbitals we have here also. So anti-bonding will be same. So here we get 1, and here we get 2 molecular orbitals of identical energy. In case of lighter element, we get the molecular orbitals in BMO in this fashion. So for your reference, let me name that this will be 2p and this will be 2p, and here it is sigma 2pz, and this will be pi 2px and pi 2py. So of course these will be the same thing, that is sigma star 2px, sorry, pi star 2px, this is pi star 2py, and this will be sigma star 2pz. So this is for the lighter molecules. So if you consider lighter molecules like boron, carbon and nitrogen, we follow this energy level diagram rather than this. For oxygen and after oxygen, fluorine, neon, and we follow this energy level diagram. So what is the difference between in these two? So if you look over the p atomic orbital, especially in a bonding molecular orbital, we have a pi 2px, pi 2py above and sigma 2pz below. Means the energy of a sigma 2pz is lesser when compared to energy of these two. Whereas in case of lighter elements, the energy of a pi 2px, pi 2py will be lower when compared to the energy of a sigma 2pz. So what is the reason for that? So here in this case of lighter element, there will be sp mixing. The term what I am going to consider here is sp mixing. So what is that sp mixing? Of course, if you consider the molecular orbital energy below this, we have sigma 2s and sigma 2s, sigma star 2s. So there will be sp mixing occur in case of a sigma 2pz and 2s. So because of that reason, to that stability purpose, 2pz will be of a higher energy, whereas in case of this there will be no sp mixing. There will be no sp mixing in case of a higher molecules, if you can consider. So this is the only change in case of homonuclear and heteronuclear what we consider. So try to know sp mixing occurs in this case of a lighter element, boron, carbon, nitrogen, and for remaining this is the in general energy level diagram what we draw. So why sp mixing occurs, let me explain that one. So if you consider the elements hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen. So already we have drawn the energy level diagram of diatomic molecules of all these elements. So atomic number 1, 2, 3, 4, 5, 6, 7, 8. Let me write the electronic configuration. 1s1 for helium, 1s2 for lithium, 1s2, 2s1 for beryllium, 1s2, 2s2 for boron, 1s2, 1s2, 2s2, 2p1 for carbon, 1s2, 2s2, 2p2 for nitrogen, 1s2, 2s2, 2p3, and for oxygen 1s2, 2s2, 2p4. That is the electronic configuration from hydrogen to oxygen I consider. So to know which undergoes sp mixing, which not undergoes sp mixing, so you need to know the electronic configuration from hydrogen to oxygen. So if you consider from hydrogen to beryllium, so only s atomic orbitals are going to be involved. So only we need to consider the energy level of 1s and 2s, and that will be same. Whereas when you start with the element boron, so in boron we have 1 electrons in 2p. When you consider carbon, nitrogen and oxygen, the 1 electron is going to be added in the same shell. Means in the 2p atomic orbital only 1 electron is going to add. What I am going to say here is, if you consider from hydrogen to nitrogen, you start from hydrogen to nitrogen, from hydrogen to beryllium, the electron density in s atomic orbital increases. The number of electrons in s atomic orbital increases. The same fashion I say the electron density in s atomic orbital increases. Whereas if you start from boron to oxygen, the electron density in s atomic orbital will be same, whereas electron density in a p atomic orbital, it goes on increasing. And in case of 2p1, 2p2, 2p3, 1 electron is going to be added. Then the pairing of electrons will be start when you consider oxygen only. Therefore you have to consider the elements from hydrogen to nitrogen. So all these are the lighter elements, but usually we consider boron, carbon and nitrogen, because from hydrogen to beryllium we don't have any electrons in the p atomic orbital. Therefore in this case of boron, carbon and nitrogen, there will be sp mixing, because in the p atomic orbital minimum 1 and maximum t electrons we have. So these atomic orbital is going to mix with the s atomic orbital. Whereas if you consider oxygen and elements more than that atomic number, that is atomic number 8, the electron density in the p atomic orbital will be greater and greater. In that case there will be no sp mixing, and this is the energy level diagram what we draw here. So this is how we followed the rules to draw the energy level diagram in case of diatomic, especially homonuclear diatomic molecules. So now what is the change we have in heteronuclear diatomic molecules, the question arises. So one example I consider, the first example, carbon and oxygen I am going to consider. So if you consider carbon and oxygen, right, so here carbon and oxygen we have, both are different atoms. So heteronuclear diatomic molecules, in that case you need to look over electronegativity property. So electronegativity property of oxygen, so this oxygen, the electronegativity property will be greater when compared to electronegativity of carbon. So electronegativity nature of oxygen will be greater when compared to electronegativity nature of carbon. Therefore energy level diagram will be not same. So what I am going to say here is, so in general if you consider 1s. So here let me explain that. So let us assume this is the energy level diagram of 1s and 1s. So we draw atomic orbitals and we draw molecular orbitals. Atomic orbitals will be of same energy. See here, the energy level this is the same in case of homonuclear, whereas in case of carbon and oxygen, oxygen is more electronegative. Therefore if you consider this is for the carbon and this is for the oxygen, the energy level of oxygen should be drawn with the lower energy when compared to carbon. Energy level of atomic orbitals of carbon has to be drawn with the lower energy when compared with the energies of atomic orbitals of carbon. So in that case the energy level diagram will be not as same as in case of homonuclear diatomic molecule. So let me explain this, what is the change. So this will be 1s atomic orbital of carbon if you consider, and oxygen I will draw bit lower. This is 1s atomic orbital of oxygen. Of course these two are of identical, almost same, not exactly, almost same energy and shape. Therefore two molecular orbitals are formed, and molecular orbitals I am going to draw in this fashion, right. So here atomic orbital and atomic orbital of 1s, and this will be molecular orbital, and this is the molecular orbital. You can call it as same sigma 1s and sigma star 1s. The same fashion has to be followed for 2s and 2p. So what I am going to say here is, here I have not drawn, if you consider the energy level diagram, here I would have drawn the 1s atomic orbital, but lower I have drawn the atomic orbital of 1s of oxygen, because oxygen is more electronegative in nature. And if you observe diagram carefully, the BMO, bonding molecular orbital, is nearer to oxygen than to carbon, isn't it? I repeat, the bonding molecular orbital of carbon monoxide in general, the middle one will be molecular orbital. The BMO of carbon monoxide will be almost nearer to oxygen than to carbon, whereas ABMO of carbon monoxide is nearer to carbon than to oxygen, because to attain this stability, as we know, if we have the pair of electrons repel each other because of same sign of electron cloud. So they try to remain as far as possible to avoid repulsion, to get a stable state. So therefore oxygen is more electronegative, therefore lesser energy level stands for greater the stability. Carbon is less electronegative or more electropositive, higher energy, and this is how BMO and ABMO is to be drawn. So try to understand, in case of heteronuclear diatomic molecules, you are not supposed to draw the atomic orbitals in the same energy level. So which is more elective, draw at the lower side, and which is less elective, draw at the higher side. And you need to consider the energy level diagram in such a way that BMO should be nearer to more electronegative and ABMO should be nearer to less electronegative. This is the change what you have to consider. So try to know, this is for the heavier elements, this is for the lighter elements, and of course heavier, lighter you are supposed to consider, but this is for in particular heteronuclear diatomic molecules. This is the theory you need to remember before moving to the example of heteronuclear diatomic molecules. First example of heteronuclear diatomic molecule, carbon monoxide I consider. We'll see molecular orbital treatment of carbon monoxide. Since it is diatomic heteronuclear, carbon is one atom and it combines with one more different atom, oxygen, and we get carbon monoxide, right? Atomic number of carbon is 6, therefore electronic configuration 1s2, 2s2, 2p2. Atomic number of oxygen is 8, therefore the electronic configuration will be 1s2, 2s2, 2p4. We have 6 electrons in carbon and we have 8 electrons in oxygen. So totally 6 plus 8, we have totally 14 electrons in carbon monoxide. Try to understand, carbon monoxide molecule contains 14 electrons, 6 from carbon atom and 8 from oxygen atom, so that totally 14 electrons we have. So 14 electrons has to be distributed in molecular orbitals. So just observe the energy level diagram of this carbon monoxide, and this is not as same as what we used to draw for homonuclear. Since we have 2 different atoms, and out of these 2, in particular example, oxygen is more electronegative in nature. There, if you consider the energy level of carbon and oxygen energy level has to be drawn with the lower fashion, whereas carbon has to be drawn with the higher energy level. So if you consider, this is the left part is for the carbon, all these are the atomic orbitals of carbon, and right part is the atomic orbital of oxygen, and the middle we have carbon monoxide. So oxygen and carbon, if you consider, so this is at the lower energy level and this is at the higher energy level. So in case of 2s also, lower energy, higher energy. In case of 2p also, see here, oxygen it is lower and carbon it is higher. This is the change what we have to consider. And if you consider the number of electrons in carbon monoxide, that is 14 electrons. I can say carbon monoxide is isoelectronic with the nitrogen molecule, N2 molecule, because in case of N2, if you consider nitrogen molecule N2, one nitrogen contributes 7 electron, one more nitrogen atom contributes 7 electrons. Totally in a nitrogen also we have 14 electrons. So carbon monoxide is isoelectronic with the nitrogen molecule. The species containing same number of electrons, we call it as isoelectronic species. So therefore these 2 are isoelectronic species. And if you just recall how we have drawn the molecular orbital energy level for nitrogen molecule as same as the lighter elements. So we used to draw sigma 2pz at higher energy level and pi 2px and pi 2py at a lower energy level. So same kind of energy level diagram I consider. So you need to think over why energy level diagram for heteronuclear diatomic molecule, in particular carbon monoxide I have drawn in this fashion. So you need to know how it is going to different from energy level diagram of homonuclear. Let me name this. So anyhow we know the energy will be increasing in this fashion. It is same for the all, if I mention or if I don't mention. So this is 1s and this is 1s, and the name I am going to write here, this is sigma 1s and this will be sigma star 1s. This atomic orbital will be 2s and this is also 2s, and this will be sigma 2s and this is sigma star 2s. And these are for 2p, you can write px, py, pz also, and this is for 2p, and these two are pi 2px and pi 2py are of identical energy, and this is of sigma 2pz which has higher energy when compared to 2px and 2py, and these two are pi star 2px and this will be pi star 2py, and this molecular orbital is sigma star 2pz, the name I have given. So now we fill the electrons. In carbon we have 1s2, in oxygen we have 1s2. So we have 2 electrons here and we have 2 electrons here. As I said, in case of MOT also you need to follow Aufbau principle, Pauli's exclusion principle and Hund's rule. So totally 2 plus 2, totally 4 electrons we have, and that has to be distributed in this section. Lower energy is filled first according to Aufbau principle. So 2 electrons here and 2 electrons here I filled. So when you compare 2s2 and 2s2, in a 2s also we have 2 electrons, in a 2s also 2 electrons. So totally 4 electrons has to be distributed in this section. So 2 electrons I fill and 2 more electrons I fill. So now I will come to very important 2p. In 2p of carbon we have 2 electrons. In a 2p of oxygen we have 2 electrons. In a carbon, this is the 2p of carbon, this is the 2p of oxygen I said. So in carbon we have 2 electrons, and according to Hund's rule, if we have atomic orbitals of identical energy, first we have to fill all the atomic orbitals with 1 electron each, and after that if you have extra electrons, the pairing of electrons starts. Whereas in case of 2p atomic orbital of oxygen we have 4 electrons. So see here how I fill the 4 electrons, 1, 2, 3, and the fourth one pairing I am going to draw here. So here we have 2 electrons and here we have 4 electrons. Totally in a 2p atomic orbitals of the carbon monoxide we have to distribute 6 electrons. So 2 from here and 4 from here, totally 6 electrons. 6 electrons has to be distributed in this section. So follow Pauli's exclusion principle, Aufbau principle, Hund's rule. Lower energy is filled first according to Aufbau principle. So 1 and 2, since they are of identical energy, so Hund's rule and 1 electrons. So 1, 2, 3, 4, and the next eligible 5 and 6. So 6 electrons I distributed here. So you got 6 electrons in a BMO of 2p molecular orbitals only. That would be the energy level diagram of carbon monoxide. So now we'll write the electronic configuration of this. So now I am going to write the electronic configuration of carbon monoxide. So as I said, you can write sigma 1s2, sigma star 1s2, or you can write since the K shell is completely filled. Principal quantum number is 1, principal quantum number is 1, and the principal quantum numbers are 2, principal quantum number is 2. So K shell is completely filled, only the L shell is going to involve in bonding, or I can say K shell is completely filled, it does not take part in bonding, only the 2s and 2p will take part in the bonding. You can write electronic configuration as K and K, and next we have what actually sigma 2s2, and next energy level sigma star 2s2. The superscript 2 represents the number of electrons in respective. Next we have pi 2px. We have a pi 2px, and in that we have 2 electrons. And we have a pi 2py, in that also we have 2 electrons. These are identical, you can mention equal sign also. And next we have sigma 2pz2. So that would be the electronic configuration of carbon monoxide. So now we will calculate the bond order of carbon monoxide. The formula will be 1 by 2 into Nb minus Na, number of electrons in bonding molecular orbitals minus number of electrons in anti-bonding molecular orbitals. Bonding molecular orbitals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 electrons we have in bonding. So anti-bonding can be identified by mentioning the star in all the terms. So here we have 1, 2 and 3, 4. So we have 4 electrons here. So 10 minus 4, 6, 6 divided by 2, you will get 3. So in between carbon monoxide, we have a covalent bond, that to 3 covalent bond, triple covalent bond we have. So the bond order is 3 in case of carbon monoxide, and this is how you can draw the molecular structure of carbon monoxide. And whether it is paramagnetic or diamagnetic in nature, if you observe the molecular orbitals, and all these molecular orbitals are completely filled, we don't have any the unpaired electrons here. So unpaired electrons contribute for the paramagnetic in nature. Since there is absence of unpaired electrons, this molecule is diamagnetic in nature. Diamagnetic in nature since the absence of unpaired electrons. So this is how the MOT of carbon monoxide you are supposed to draw in this fashion. The only change is the energy level diagram, you remember, and electron filling and writing the electronic configuration, bond order, and the property will be as same as in case of homonuclear diatomic molecules. That is the first example, carbon monoxide. Second example, nitrogen monoxide or nitric oxide, NO. We have two different atoms. One is nitrogen and one more is oxygen, and these will combine, we get a molecule nitrogen monoxide. Nitrogen atomic number is 7, therefore electronic configuration is 1s2, 2s2, 2p3. Whereas oxygen atomic number is 8, therefore electronic configuration 1s2, 2s2, 2p4 we have. So 7 electrons from nitrogen and 8 electrons from oxygen. Totally the nitrogen monoxide NO has 15 electrons. So 7 from nitrogen and 8 from oxygen. Totally we have 15 electrons. So these 15 electrons has to be distributed in molecular orbital energy levels. So now observe the MOT diagram of a nitrogen molecule. Everything is same since this belongs to heteronuclear diatomic molecule, and when you compare nitrogen and oxygen, oxygen is more electronegative in nature, therefore oxygen atomic orbitals I have considered with lower energy level, whereas nitrogen atomic orbitals I considered with higher energy level when compared to oxygen. Or you can consider the BMOs will be nearer to oxygen and ABMOs will be nearer to nitrogen. But the change if you observe in case of 2p, so in the previous case of carbon monoxide, I have drawn a 2pz at the higher energy level. Now sigma 2pz at lower energy level I have considered, because in this case there will be no sp mixing. So totally we have 15 electrons. So 15 electrons, quite electron density will be greater in case of 2p. In case of nitrogen monoxide, when you compare with the carbon monoxide, therefore this is the suitable energy level diagram you need to consider. So now we fill the electrons. In nitrogen 1s2 we have, so 1s2 2 electrons. In oxygen also we have 1s2 2 electrons I fill here. So totally 4 electrons has to be filled. So this is the fashion how you are supposed to fill the electrons. In a 2s of nitrogen, 2s of oxygen, we have 2 electrons. So here I fill 2 electrons and here I fill 2 electrons. In the molecular orbitals, 4 electrons I fill here. So try to know the left side belongs to atomic orbitals of nitrogen and right side belongs to atomic orbitals of oxygen. In the middle we have molecular orbital of nitrogen monoxide. Now in a 2p of nitrogen we have 3 electrons. Follow the Hund's rule. So 1, 2, 3. In a 2p of oxygen we have 4 electrons. Follow the Hund's rule. Therefore 1, 2, 3, 4. 4 electrons we have, and we have plus 3 electrons. Totally 7 electrons has to be distributed in this 2p section. 7 electrons. Okay. So how you fill the 7 electrons? Out of 7, 2 is going to be filled here. 1, 2, 3, 4, 5, 6. Sorry. 5, 6 and 7 will be in this case. So pi star 2px has 1 electron. So how I filled the 7 electrons? 1, 2, 3, 4, 5, 6 and 7 we have. So that is how electronic configuration has to be filled. And now I write the electronic configuration of this nitrogen molecule. Since K shell is completely filled, KK I write here, or instead of that you can write sigma 1s2 sigma star 1s2 also. Since K shell is filled, that does not take part in bonding, and you can skip this drawing diagram also, there is no big deal in that one. So KK, and then we have sigma 2s and we have 2 electrons in that MO, and sigma star 2s and we have 2 electrons in that. And the next energy level what actually that is a sigma 2pz, and we have 2 electrons over there, and pi 2px, we have 2 electrons over there, and pi 2py, and we have 2 electrons also in that molecular orbital. We have one more orbital of a higher energy, that will be pi star. Okay, what actually pi star 2px, but we have only one electron in that case. So that is the electronic configuration. Now we'll see the bond order of nitrogen monoxide. The formula is 1/2 into Nb minus Na. Now we count the number of electrons in bonding molecular orbitals. So N star 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons we have in bonding molecular orbitals, and anti-bonding. So 1, 2, 3, 4, 5 electrons we have in anti-bonding. 10 minus 5 you get, therefore the bond order is 5/2, or you can write it as a 2.5. So bond order is 2.5. And now we'll see whether it is paramagnetic species or diamagnetic species. And you have to observe the molecular orbital energy level diagram. We have such MO, that is pi star 2px, where we have unpaired electrons. So since there is presence of unpaired electrons, this particular species is paramagnetic in nature. So this species is paramagnetic in nature. So try to know that one. NO belongs to heteronuclear diatomic molecule, and the electronic configuration is in this fashion what I have written, and the bond order is 5/2 or 2.5, and this molecule is a paramagnetic species because of presence of one unpaired electrons in a pi star 2px. That would be the MOT of NO. Example number 3 is an ion NO plus nitrosyl ion it is. So we have a nitrogen and we have oxygen, but we have a charge over there, plus charge we have. That indicates one electron has been lost from a molecule of NO. As we know, in case of nitrogen we have 7 electrons, in case of oxygen we have 8 electrons. Totally nitrogen monoxide NO molecule contains 15 electrons. But we don't have NO, we have NO plus. One electron has been lost. Therefore, if you consider the NO plus, in NO plus, totally we have 15 electrons, one electron has been lost, therefore we have 14 electrons. So in NO plus we have 14 electrons. If the question is NO minus, one electron has been added, therefore in that case 16 electrons you need to consider. So one electron has been lost, so from 15 one has been lost, means 14 electrons we have. So 14 electrons has to be distributed in this section. So in case of 1s and 1s of both atoms, we have 2 electrons. I fill 2 electrons here, and 4 electrons in the molecular orbitals by following the rules. In a 2s of nitrogen, 2s of oxygen, we have 2 electrons. So here I write 2 electrons, and here also I write 2 electrons. Totally 4 electrons has to be distributed in this section. So try to know, the left part is for nitrogen and right part is for oxygen. In between we have NO plus molecular orbital region. So in a 2p we have 3 electrons, isn't it? So in a 2p we have 2 electrons, and in a 2p of oxygen we have 4 electrons. Totally 4 plus 3, 7 electrons we have. So there will be loss of electrons, means the loss of electron will be from valence shell only. So we don't have 7 electrons in 2p, we have 6 electrons. So these 6 electrons how I represent? So 3 in case of a nitrogen and 3 in case of oxygen I represent. Actually I would have drawn one more electron if it is NO, but it is NO plus we have 1 electron has been lost, therefore 1 electron is going to be lost, therefore I have written only 3 electrons in case of 2p of oxygen. So now in a 2p section, totally we have 6 electrons, and 6 electrons has to be distributed. So out of 6, 1, 2 I will include here, because sigma 2p is of lower energy. Next higher energy, these two are identical. So 1, 2 and 3, 4, 5 and 6. So all 6 electrons is going to be filled in a BMO section only. So we don't have any electrons in ABMO section. So we'll write the electronic configuration of NO plus. Since the K shell is completely filled, it does not take part in bonding. Therefore KK I write, then sigma 2s2 I write, and sigma star 2s2, and then we have a sigma 2pz2 we have, and next pi 2px 2 you need to consider, and one more is pi 2py 2 you need to consider, and we have 2 electrons in 2px also, 2 electrons in 2py also. 1 electron has been lost. Actually the electron from pi star 2px is going to be lost, so we will get electronic configuration in this fashion. So we'll see the bond order. Bond order is going to be calculated using the formula 1 by 2 into Nb minus Na, number of electrons in bonding molecular orbitals, number of electrons in anti-bonding molecular orbitals. Bonding molecular orbitals will see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons we have in bonding, and we'll see anti-bonding, so star 1, so 1, 2, 3, 4, and we don't have any electrons here, therefore 10 minus 4 you will be getting 6, and 6 divided by 2 you are going to get 3. So there will be 3 covalent bonds in NO plus, and the bond order is 3 we have. And now you try to know what about the magnetic properties. So if you consider MOT diagrams, we don't have any unpaired electrons, therefore this belongs to diamagnetic in nature. This belongs to diamagnetic in nature, since there is the absence of unpaired electrons, and that is all about the molecular orbital theory of nitrosyl ion. Finally, we'll compare the two theories what we studied to know the covalent nature in molecules. The previous theory was valence bond theory, and recently I discussed molecular orbital theory. So valence bond theory and molecular orbital theory. So we'll see what is the common points we studied in these two different theories. These two theories are approximations only. So based on the practical concept of the molecules, and the scientist explained the approximations respectively in case of VBT and MOT. And in both cases, in VBT also we considered atomic orbitals, in MOT also we considered atomic orbitals, and there will be overlapping of atomic orbitals so that a stable molecule is going to be formed. And here, greater the overlapping and greater will be the stability. This theory's concept is explained by both theories VBT and MOT. And try to know, in case of VBT, we have said that there is no existence of He2 molecule, and in case of MOT molecular orbital theory also, since if you consider He2 molecule and the bond order 0 we got, therefore He2 molecule does not exist in nature. And in both cases also, we compared the energy levels of atomic orbitals and how the stability of molecule is going to be formed. And one point you just carefully observed, in case of VBT, we explained only the oxygen molecule contains 2 covalent bond, whereas in case of MOT, not only the double covalent bond, we explained the paramagnetic nature. This is a very important point, or I can say one of the demerit of VBT is VBT cannot explain the paramagnetic nature of oxygen, whereas in case of MOT, if you just recall, the bond order we got 2, and we have 2 unpaired electrons in a pi star 2px and pi star 2py of oxygen molecule. Therefore oxygen molecule is a paramagnetic according to MOT, and that is the one more advantage over the VBT what we have for MOT. And try to observe, in VBT the resonance concept was very important one, that was the integral part in case of VBT, whereas in case of MOT we have not considered the concept of resonant to explain the properties of the covalent nature of molecules. So by knowing both VBT and MOT, I explained the properties of a covalent nature of the molecules, and that would be the complete end of the chapter, chemical bonding and molecular structure.